Hello everybody. In the last class we saw certain application of shift register, and there we saw that a feedback of shift register, the serial out as a serial in can give rise to sequence generation, ring counter, Johnson counter. We shall look at what is called linear feedback shift register in this particular class and its different uses. Okay. So, by linear feedback shift register, what we actually mean that the shift register outputs, say it is a say length 8 we consider, x1, x2, x3 etc., like up to say x8. Okay. So, it is going to a block where there is a feedback function, and that feedback function is generating an output, okay, and that output is getting fed as serial in. Okay. And when we say linear, so this is the general case. Linear means this function has got a linear relationship. The equation that we are having is a linear relationship. Okay. So, in this case we write it in this manner: C1 x1 C2 plus C2 x2 to C8 x8. Okay. And these coefficients are either 0 or 1. Okay, it is a binary world. So, it is 0 or 1. So, 0 means there is this value is not used. Okay. So, in another sense, there is no tap from this shift register output to the this feedback junction function generation logic. Okay. So, that is not there. Okay. And if there is a 1 present, that means that particular tap is present. So, that is how these CIs are defined, either 0 or 1 tap is present or tap not present, and this plus is the sum operation which is obtained through XOR. Okay. So, this is the way the circuit is developed. And if we look at an example, so y is x1 plus x2 plus say x7, right. What does it mean? So, x1, x2 and x7. So, these 3 taps are used, and they are, these 3 inputs are summed up here, these 3 outputs of this shift register is summed up here and fed as input to the input y as serial in. Okay. For example, if the the shift register is initially loaded with this value 1 0 0 1 1 0 1 1, okay, then x1, x2 and x7 are this value, the one in the bold, right. Then y will be 1 XORed with 0, XORed with 1. So, the value is 0. So, 0 will be fed back. So, with clock trigger what will happen? So, this 0 will come here. So, everything else will get shifted 1 0 0 1, 1 0 1 will come over here. So, at that time your x1, x2, x7 are the one in the bold again here 0 1 0. So, 0 1 0. So, now the value is 1. So, next value 1 will be getting in, okay, and rest of the values will be shifted. Okay. And when we say non-linear, that means other than some operations, so this is x1 and x2 or then some x7. So, these are the things that comes under non-linear feedback, which we are not discussing here. Our topic is linear feedback shift register. Okay. So, what we have seen that is redefined in a manner by which we introduce the term feedback polynomial. Okay. So, in this, instead of x1, x2 up to x8, we represent the output of this shift register of length 8 as x to the power 1, x to the power 2, x to the power 3, x to the power 4, etc. up to x to the power 8. As if each one of them is delayed by 1 8. So, delayed by 1 8 d, delayed by 2 unit d into d square. So, d cube d4. So, this is the idea. Okay. So, in this sense you have got x to the power 8 up to here, right, and the input to it is not delayed, it is the it will come to the output after one clock trigger, isn't it. So, this input is represented as x to the power 0 or 1, x to the power 0 or 1. So, this 1 you will see in the polynomial that or the function that is getting represented, and usually in many cases, since it is length 8, the requirement is of that of length 8. So, x to the power 8 is also would be visible if it is of so if it is of length n, so x to the power n is also expected to be there, but there could be another way the polynomial can be generated, okay, without that. And in between, wherever the connection is there, that means these Ci values are 1, the tap is there, otherwise it is 0, okay, right. So, for n bit shift register, the degree we say will be of n, 8 bit, here the degree is 8, and these are some examples, okay. And if it is x8, x7 and x1, okay. So, x8, x7 and 1. So, x8, x7 and 1 is this one. So, what does it mean actually? So, these two are getting XORed, okay, and fed as input. So, this is the meaning of this polynomial. Is it okay? Tap from bit 7 and 8 are XORed and fed as serial input to bit 1. Now, such an arrangement, okay, can give rise to, can generate pseudo random sequence. Sequence generator we have seen. So, where we had seen a particular length, if it is 8 bit, it is 8 bit long it was, right. Here we see what happens when we connect in a particular manner. So, here there is a 4 bit shift register, okay. So, this 4 bit shift register, this S and T is XORed and fed as serial in. So, in terms of polynomial, feedback polynomial, just now we have defined, this is x to the power 3 and this is x to the power 4, okay, and this input is 1. So, we will be representing this as x to the power 4 plus x to the power 3 plus 1, clear, okay. This arrangement can be rewritten as this, the meaning is the same, okay. So, if this thing happens, then let us see how with clock these states will evolve, okay, and what will be the serial in each case. So, it is, if it is initialized with say 0 0 0 0, what will happen? So, if it is all 0 0 0 0, so 0 0 XORed output is 0, okay. So, this 0 will be fed in. So, again next value will be 0 0 0 0, so it will remain locked. So, it is not to be initialized with 0 0 0 0, okay. So, let us consider instead of all getting cleared, all was preset, okay, all the flip flops were preset, okay, and it was initialized with 1 1 1 1. If there was no preset option, then it was serially in or parallelly loaded, but somehow we have initialized the shift register with a value 1 1 1 1, okay. Then what will happen? This S and T are XORed, so 1 and 1 is XORed, so serial in will be 0, so next value will be 0 1 1 1. After that, this 1 and 1 again this 1 and 1 XORed, it is 0, so again 0 comes and the rest of the things get shifted, so it is 0 1 1. So, then this 1 1 again 0, so this is 0 0 1. Now, 0 and 1, this is 1, so this is 1 0 0. So, this way you will continue, you can work it out, and you can see unlike the sequence generator which was of length 4, in this case this output which is the you can take as final output of 8, it continues up to a length which is 15. After that again it starts repeating. After that it starts repeating, and the numbers you can see over here, these zeros and ones, it is what is known as pseudo random, okay. It is not exactly random in the sense, because it repeats after some time, and if you have number of these n bit shift register, if the value of n is large, then of course you can understand that the length will be very large, and the formula that is used for such case is the maximal length that is possible is 2 to the power n minus 1. 2 to the power n minus 1. All these 0, 0, 0, 0, that particular state is not acceptable. Okay. Rest of the things are getting, rest of the states are getting circulated. Okay. So, with a higher values of n, you can understand that these will get repeated after a long value. Okay. After a very, the sequence will be very long. Okay. And almost equal probability of zeros and ones that is present in this particular sequence. Okay. Clear? So, this is a one particular way you can generate pseudo random sequence using shift register. Okay. And you require minimum hardware additional hardware, and you can move very fast. Okay. These things can be done in a very fast manner. Now, it is to be noted that the feedback that you take, okay, any kind of feedback will not give maximal length. Okay. So, for example, again for that 4-bit shift register we are talking about, instead of x4 and x3, okay, if it is x3 and x2, they are XORed and fed as serial in. So, the corresponding polynomial is x3, x to the power 3 plus x to the power 2 plus 1. Okay. And we initialize with say 1 1 1 1, then the serial in is 0. So, 0 1 1 1, and that way you continue. We shall see that over here it becomes, okay, 1 1 1 0. Okay. After that again this 0 comes over here, this is t, okay, this is q r s t, this t comes here. So, it becomes 0 1 1 1. So, this 0 1 1 1 again repeats here, and of course, after that it will repetition will start. So, 1 2 3 4 5 6 7. So, this cycle length becomes 7. Earlier when it was taken from x3 and x4, x to the power 3 and x to the power 4, and it was 1, it was a maximal length that was 15 possible, 0 0 0 0 was ruled out, okay, because it will remain locked. So, this is to be noted, and that gives us brings us to the discussion on primitive polynomials. So, not all polynomials will give us maximal length. So, the one that gives us the maximal length are called is called primitive polynomial. Okay. And so, the example that you can see, so these are the polynomials that requires minimum number of XOR gates for a given degree. So, we have provided a table. So, for degree 2, 3, 4, 6, 7, okay. So, x to the power n plus x plus 1, that will give a primitive polynomial. This is not the only one, I shall tell more about it shortly. So, but this will give you a primitive polynomial, right. So, for example, if it is say 7, so x to the power 7 plus x plus 1 1 is the input that is coming here. So, 7th flip flop and the first flip flop output, right, XORed together and fed as input, it will give a maximal length, and maximal length will be 2 to the power 7 minus 1. Okay. So, that is how it is there. So, for 5 x to the power 5 plus x to the power 2 plus 1. So, 8, 9, 10. So, this is what has been arrived at after checking with different combinations. Okay. Now, in each of these cases, when you look at it, right, and what you can find that the necessary condition, it is not sufficient, but it is required that number of taps are even. Okay. Number of taps x to the power n and x. So, x, that is x to the power 7 and the first flip flop and 7th flip flop, 5th and 2nd, 8th, 6th, 5th and 1st. Okay. So, 9th and 4th, 10th and third. Okay, so we have shown it up to say 10 degree, but you can extend and you can see that always the number of taps are even. Okay. And the other important thing is the tap numbers are co-prime, like 7 and 1, 5 and 2, 8, 6, 5, 1, 9, 4, 10, 3, relatively between them, okay, there is no common divisor other than 1. Okay. So, that is a necessary condition, but it is not a sufficient condition. The other thing important here is if the tap sequence of a n-bit linear feedback shift register generating primitive polynomial is n, m, l, k and 0. N means that is the, if it is a degree 8, okay, the last flip flop, so that is n, and 0 is the input that is coming here, x to the power 0. So, n and 0 are there, and in between these are the different taps. Then if this, that gives a primitive polynomial, then n minus n, n minus m, n minus l, n minus k, n minus 0, right, which the first one will give you 0 and the last one will give you n. So, basically they do remain, okay. And other values is just n minus the other one, the particular tap number, okay. That will also give a primitive polynomial. That will also give a maximal length sequence and pseudo random number getting generated of that particular length. Okay. For example, in this case, so if x to the power 5 x square plus x square plus 1 is a primitive polynomial, then n minus m is x to the power 5 minus 5, 5 minus 2 and 5 minus 0, right. So, x to the power 5 plus x to the power 3 plus 1 is also a primitive polynomial. So, if you take it from 5 and 3, XOR it and feed it as input, that will also generate maximal length, in this case 2 to the power 5 minus 1 long sequence, okay, which will repeat, okay, pseudo random sequence. So, what we had discussed so far is constitutes external feedback. Okay. So, there can be linear, there can be internal feedback also if provision is there, by which these polynomials can be generated and implemented. Okay. So, internal using internal feedback, if we are implementing the polynomial x to the power 4 plus x to the power 3 plus 1, okay, which was maximal length in case of the external feedback which we have already investigated. Okay. So, then how it would look like? So, x to the power 4 and x to the power 3, they are XORed and fed as input to the flip flop over here. Okay. And of course, x to the power 4, this is coming over here as 1. X to the power 0. So, this is how it would look like with internal feedback. Okay. And with this internal feedback, again, if you look at an initialization with say 1 1 1 1, right, and then you can see for first few cases you can examine. So, here S and T are XORed. Okay. S and T are XORed 1 and 1. So, the output is 0. So, S and T. So, this output is 0. So, 0 will be fed back here. So, next clock, right, this is becoming 0. And this was 1, 1 is fed back here 1. So, these other two 1s are getting pushed. Okay. This 2 1 is getting pushed here. This 1 is coming over here and 1 1 XORed is 0. So, that is getting 0. Is it okay? So, next this 0 will come over here like this. Right, these 2 1 are getting pushed over here, and now 1 and 0 XORed is 1. Okay. So, this 1 XORed 0 is coming over here. So, this is the way it will evolve. Okay. And if you progress, you can see that it is coming to 4 1s again after 15 clock trigger, after 15 clock pulses. Okay. So, this also x to the power 4 plus x to the power 3 plus 1 gave maximal length for external feedback. For internal feedback also, that we see that it is giving maximal length. Okay. So, But in this case, the pseudo random sequence that is getting generated is 1 0 1 0 1. So, whatever you see over here, and for the other case we saw something else. Okay. So, that number getting generated and fed as serially in could be different, but maximal length is there for both the cases. Okay. So, this is one important thing we take note of, that primitive polynomial for external feedback also works as maximal primitive polynomial for internal feedback, okay, and generates pseudo random sequence. Clear? Now, we look at again this particular arrangement configuration. Earlier it was actually evolving only from internal the state values and the feedback that is getting generated. Now, the feedback is there. In addition, we are putting an external input, okay, and we would like to see if it is of any use. Yes, it is of important use in error control code generation, okay, and this is used in what is called cyclic redundancy check code, CRC code now. Okay. So, I shall take you through an example and see how it is useful. So, the polynomial here is used x to the power 3 plus x plus 1, right. So, that means this is 1 to 3. So, this one, okay, this one, first one, it is fed back, okay, this x3 x1. So, this through internal feedback, this is fed here, and this one that is coming over here, that is getting absorbed with the incoming data stream, okay, which we call as a message, which we want to code. Is it clear? So, x3 x plus x absorbed here, going here, and 1 is coming over here, which is now getting absorbed with the incoming data stream, right. Now, the message that we are having, let us consider it is a 7-bit message. These flip flops are initially all cleared, right, in this register, shift register, okay, and to this 7-bit long message we append 3 zeros. We append 3 zeros, signifying the values that are present here, signifying the initial values of this shift register. Okay, right. So, now this is the input data stream, 7-bit and 3 appended with 3 zeros. Okay. So, now how this particular circuit evolves with time, with clock pulses. So, this is the clock pulse 0, this is serial in. So, initial value is 1. So, this is the 1 that you see here. So, these are all 3 zeros. Okay. Then what happens? This 1 and 0, right? This is 0. So, D1 is serial in and XORed with Q3, serial in XORed with Q3. D2 is this one, okay. Q1 and Q3 getting XORed, and D3 is just whatever is Q3 output, that is going as Q2, okay. And always we know for D flip flop whatever is the Dn, that is becoming Qn plus 1 next clock value, okay. So, we can examine it in this manner. So, the first case serial in is 0, serial in is 1 and Q3 is 0. So, the value is 1, right. So, what will go to Q1 in the next clock is 1, okay. Then Q3 and Q1 XORed is 0, Q3 and Q1 XORed is 0. So, next clock it becomes 0, and what will Q3 will get? Q3 will get whatever is there in D3, D3 gets Q2. So, this is the one that will be there. So, next value will be 1 0 0. After that 1 comes as the serial input. So, 1 and 1 serial in and Q3. So, 1 and 0. So, 1 comes here. Then Q1 and Q3, right. So, 1 and 0. So, this is 1, So, 1 comes here in the next clock and Q2 comes to Q3, okay, in the next clock. So, that becomes 1 1 0, then 0 comes here. So, that way it continues and you include these zeros also. Okay. So, 0 to 9, so 10 clock pulses are there. Once we complete these 10 clock pulses, right, the value over here what we see is 0 1 0, that is the remainder. Okay. So, that remainder now we attach as check bits to these 7 message bits. Okay. If the message bit was less than that, then we would have or more than that, we will continue accordingly. But always we will be in our scheme of things, these 3 zeros will be there. Okay. Right. So, now this is the what is getting transmitted, right. These message bits are getting transmitted. At the receiver end, what will you do? So, receiver end, now these bits, okay, whatever is there will be given as input. The circuit will be the same and it will be initialized with 0 0 0, okay, and we will progress in the same manner, exactly the same manner, the way it has progressed at the transmitter end. And at the receiver end, when if every bit is appropriately received, no error is there, then the remainder will become 0 0 0. Okay. If the remainder is anything other than 0 0 0, okay, then that means there is a error here. There is a error here in the incoming stream. Okay. And this CRC code is specially useful for detecting burst error. Burst error means because of noise and all, more than one bits, consecutive bits have have become wrong. Okay. So, error has got into consecutive bits. Okay. So, this is the CRC code generation, and then its at the receiver side its detection. Okay. And this is the way the check bits are coming, and there the shift register is useful. There are many applications of LFSR. So, here I have listed a few, and majority of them from its ability to generate pseudo random sequence. If the counter does not require states to be like 0 0 0 1 0 0 1 0, that kind of these sequential numbers increment is not required, any kind of states can be there, and then a first counter can be made of sufficiently long length. So, that is within bit we can go up to 2 to the power n minus 1, and the other use of it is in test pattern generation of which can be used for testing the faults in application specific integrated circuits. Scrambling is another use of LFSR output. These pseudo random sequences can be XORed with the message bit, and the resultant signal pattern would look more noise like. Okay. And the reverse can be done at the receiver end to get back the original message, and it is used in cryptography also, where the initial seed from which the pseudo random sequence is generated can serve as a cryptographic key and can be used for encryption first and at the receiver side for decryption. And you have already seen its use in error control code, the cycle redundancy check, the check bits, the way it has been placed, and CRC 16 is one popular such thing. CRC 32 is also there. For example, x to the power 16 plus x to the power 15 plus x square plus 1 could be one such polynomial, and it can detect up to 16 burst error and many other types of errors. Okay. So, with this we conclude, we have seen that LFSR can be used and to generate through primitive polynomials, pseudo random sequences of sufficiently long length. Okay. And these primitive polynomials need to have even number of taps, and tap indices need to be relatively prime. This is a necessary condition, not sufficient. And CRC code is useful for error control as error control code, and LFSR can be used in cryptography and scrambling, test pattern generation, and many other areas. Okay, thank you.